Hello, students. Let me see if I can get this in one take. So we are doing lesson 6, finite and infinite decimals. Like Infinity War that goes on forever and ever, we have infinite decimals and finite decimals, so decimals that end. So we're going to prove that real numbers with a finite decimal expansion are precisely the fractions that can be written with a denominator that is a power of 10, and realize that any fraction with a denominator that is a product of twos or fives can be written as an equivalent form with a denominator that is power of 10. So these are connected because what is 2 times 5? 10, right? So if you have a fraction and the denominator is some sort of power of 10, 10, 100,000, whatever, it's really easy to make it into a fraction. You just say, you count the number of zeros in the bottom, and that's how many decimal points you have. So so if you have 375 over 1,000, that's 3 zeros. So that would be a decimal 0.375. Okay, so it's pretty easy. So 54 divided by 20, will it be terminating or repeating? So think about 20. Can it be broken down into 10, or can it be broken down into twos and fives, right? So let's try long division. 54 divided by 20. So this is 54 divided by 20. You would write it this way in your calculator. You would write 54 divided by symbol 20. So that is 2.7 because 20 goes into 54 two times. 2 times 20 is 40. 54 minus 40 is 14. 2 goes into 14 7 times. 2 times 7 is 140. It's 14. Okay. So the decimal for 54 over 20 is 2.7. There's a long division calculator that does this work for you. I'll share that with you later. You can also just use your calculator. If you type in your calculator 54 divided by 20, you get 2.7. Okay. Will 7 over 8 be terminating or repeating? Well, what is 8 factored out, right? 7 divided by 8 is 8 goes into 7 0 times, bring down the 0, 8 goes into 70, 8 times, 64, etc., etc., etc. So you can do this by hand, and when this starts repeating, that's when you get to the end. Or when you get to a 0 remainder, that's when you get to the end. Okay. 8 divided by 9, will it be terminating or repeating? So 8 divided by 9, 9 doesn't go into 8, 0, bring down the 0. 9 goes into 80, 8 times. 8 times 9 is 72. 80 divided by 72 is 8. Bring down the next 0. 8 times 9 is 72. 80 minus 72 is 8. Bring down the next 0. 9 goes into 80, 8 times. 8 times 9 is 72. Notice how we keep repeating? As soon as we start repeating, this is called a repeating decimal. Okay. These decimals were terminating decimals because they stopped. This decimal is repeating because you can continue this forever and you'll keep getting 8s up there, and you'll keep getting a 72 minus 80 minus 72 equals 8 going down here. Okay. 22 divided by 7, will it be terminating or repeating? So this one goes on like this: 3.14287, but it's going to end eventually. I just ran out of room. It's a really, really long decimal, but it will end. Actually, this is where it's repeating. See how the 1, I had 22 minus 21 is 1. Here I got 50 minus 49 is 1. But when I get this 1, the next number I bring down will be a 0, and I'll be in this loop again. So this will repeat 1, 4, 2, 8, 5, 7 in that order again and again and again. So this will be 3.142857, 142,857, 142,857. You'll do that forever and ever and ever. Okay. So what's the difference? 54 divided by 20 and 7/8 were both terminating decimals, because if you factor them, you get a factor of 2 and 5. So this has a factor of 2 times 2 times 5, and this has a prime factor of 2 times 2 times 2. I used the prime factorization calculator. I'll let you do that one as well. 9 factors into 3 and 3. So notice these only have 2's and 5's. This has a 3, and here there isn't even a prime factor tree because 7 is a prime number, and 7 is not 2 or 3. So if I do all the prime factorization and the numbers are always 2's and 5's, then I will eventually get to the end of the decimal. If I do prime factorization and I get any other number, even once, then I will have a repeat. Okay. So some real funky tricks. So if I have 3/8, 8 can be factored into 2 times 2 times 2. So for each 2 or 5 in the denominator, I multiply to get a 10. So if I have a 2, I've got to multiply by 5, I get a 10. So I'm going to take the 3 2's and I'm going to multiply each of them times 5. But I've got to multiply the top by 5 3 times, just so I'm not changing the number. So I'm just multiplying by 1. I'm multiplying by 5/5 times 5/5 times 5/5. So 3 times 5 times 5 times 5, that's 3 times 125. 2 times 5 is 10. 2 times 5 is 10. 2 times 5 is 10. So I've got 3 times 125 over 10 times 10 times 10. That's 375 over 1,000. If we remember from earlier in the year, 1,000 is 10 to the power of 3. So there's going to be 3 decimal points in my answer, and the decimal is 0.375. So I got the 375 from the top, and I got the fact that it was 3 decimal points here. 1, 2, 3. Works with any number as long as that number can be factored into 2's or 5's or a combination of 2's and 5's. So 80 factors into 2 times 2 times 2 times 2 times 5. Put in your calculator. 2 times 2 is 4, times 2 is 8, times 2 is 16. 16 times 5 is 80. So now I'm going to do 2 times 5, 2 times 5, 2 times 5, and I've got a 2 times 5 here. So 2 times 5, 2 times 5, 2 times 5, 2 times 5. So I added these 3 5's in. I've got to multiply by 3 5's on the top. 7 times 5 times 5 times 5 is 875. 10 times 10 times 10 times 10 is 10 to the 4th power, because I got 4 10's there. So I've got 4 decimal points here. I've only got 3 numbers here, so I have to add an extra 0. So it's 0.0875. Excuse me. It does not work on fractions where the denominator cannot be factored into 2's and 5's. So 34 can be factored into 2 times 17. 17 is not a 5, so if I put this in my calculator, 19 divided by 34, I would get 0.55882352941117, and kind of goes on and on from there. Okay, but the important thing for right now is to know it is not a repeating number. Okay. So, summary. There are 2 types of decimals we can get from a fraction. We can get a terminating decimal, or a decimal that ends, and these decimals will have factors, prime factors of only 2's and 5's. Or I can get repeating decimals, decimals that don't end but have a repeating pattern. We'll learn about repeating decimals later. We will not get irrational numbers. We will not get decimals that go forever without repeating or without end. We will either have decimals that end or decimals that repeat, even if the numbers that repeat are a lot of different numbers. Okay, that is the lesson.